Hi everyone, this is Mrs. Cooper and this is our presentation on John Dalton. Please take out your notebook and a pen so you can start writing notes on this prominent scientist. John Dalton was born in Cumberland, England in 1766, and he was a lot of things. He was a chemist, a meteorologist, a physicist, and he was also a teacher. He started teaching at the age of 12, very, very young. One of his major works, he developed gas law. He worked on color blindness, but one of the things that he's most famous for is his work on the development of modern atomic theory, which is what we're interested in this class. So John Dalton, he worked with gases, he studied gases, and he concluded, based on his observations and experiments, that matter was composed of small individual particles. And to name these particles, he went back to Democritus and he borrowed the term atomos, which means particles that cannot be broken down into smaller particles. These are indivisible. John Dalton was one of the first scientists to actually suggest the concept of atomic weight and ratio. And this concept, the ratio concept, is very important because it tells us the way that elements combine to form chemical compounds. For example, here we have a water molecule and we have the chemical formula H2O. This means that every oxygen atom will be combined with two hydrogen atoms to form a water molecule. And water will be the same all over the world. So this is a universal concept. So how do we move from the concept of ratio to the actual concept of a single atom? Well, people who have studied John Dalton's lab notebooks have suggested that while he was working on the law of multiple proportions, he came up with the idea that this chemical combination needed something with a definite and characteristic weight. So that's how he comes with the concept of atomic weights. And right there is the concept of the atom. So we need a particle that cannot be divided and that it will share. For example, here we have two hydrogen atoms. So this have to be exactly the same. We're talking about the same kind of atom right here. So that's how John Dalton, by studying gases in the atmosphere, comes up with the concept of the atom. John Dalton is able to publish his work. This is the first time he publishes something related with the atom, and this was on his paper on the absorption of gases. And here he writes, "Why does not water admit its bulk of every kind of gas alike? This question I have duly considered, and though I am not able to satisfy myself completely, I am nearly persuaded that the circumstance depends on the weight and number of the ultimate particles of the several gases." So here we see he's talking about this weight and the number, which is part of the ratio, and the particles, which he will later refer to as atoms as part of his atomic theory. Now we're going to talk about the main points of Dalton's atomic theory. So number one will be all matter is composed of atoms, which are extremely small particles. Number two is atoms cannot be created or destroyed. They cannot be subdivided into smaller particles. So the atom will be the smallest particle we can find according to Dalton. Number three states that all atoms of the same element are identical, and this means that they have the same size, mass, and other properties. Number four is very similar to number three, and this states that different elements will have different types of atoms. So for example, we were talking about water before in our video, and we can say now that the hydrogen atoms will have the same size and mass, so again the concept of atomic weight. However, they will be different from the oxygen atoms. Number five states that chemical reactions occur when atoms are rearranged. So the concept that they cannot be created or destroyed means that atoms can only be rearranged between one another to form different compounds. And that's part of the last main point of Dalton's atomic theory, which is number 6, compounds are formed from atoms of the constituent elements. So here we have the 6 main points of Dalton's atomic theory, which are very important, and we will be using this later on to compare them to the different scientists that worked on the atomic model. Following the 6 main points we talked about, we can draw or be able to determine a model for Dalton's atomic theory as a sphere. This sphere will be indivisible, and here we don't know if this is hydrogen or oxygen or nitrogen, but we know that for this, in case it were, let's suppose we're talking about carbon, then this carbon atom will share the same characteristics with other carbon atoms, but it will differ from the other elements. So Dalton's model is basically a sphere that cannot be subdivided into smaller particles. Thanks to John Dalton's work, we're able to know now that elements are composed of only one kind of atom and compounds are composed of different kinds of atoms. Here we see a table that Dalton published in 1808, and we see on the top that we have the elements, different elements, and then we have binary molecules, ternary molecules, quaternary molecules, and so on. For example, a binary molecule will have two different elements together, which will be a compound, as we know now. And here is a very interesting work. This is Dalton's table of atomic weights, and we see the element hydrogen, which is the one he in the last. Here is the first one. Okay, so if we go back to the first figure, hydrogen he assigned as the first element, and he gave it the atomic weight of 1, which will be very accurate, I would say. The first elements he worked with were hydrogen, oxygen right here. He gave that a 7. He also worked with nitrogen, carbon, and sulfur, phosphorus as well. And later on, he started adding more elements, as we can see here. So this was published also in 1808, and it's a very advanced work for his time. And finally, we have the last part of our video, which are some interesting facts about John Dalton. John Dalton was colorblind, and that's why this deficiency has the name Daltonism. If you are colorblind, you cannot probably see, well, you will not see 4, 7, and 8 in this circle right here. That's an inability to see color differences. John Dalton, as we mentioned before, he's known for lots of things, and one of them was his work on gases. He has a law that he came up with, which is Dalton's law, and this one states that the total pressure of a gas will be equal to the partial pressures or the individual pressures of the gases in the mixture. And finally, here we have a link on John Dalton's studies on meteorology, and this is a cool video. It shows how he had a journal, a diary, where he kept about 200,000 entries for the weather. So that's good data keeping in a lab notebook. So we're gonna watch this video and hope you learned something from it. Thank you for watching, and I'll see you in class.
One of the most familiar ideas in the world is that matter is made of atoms, and that chemists study these atoms, and many of you no doubt have used chemical symbols and formula. But when you ask where did this come from, it all came from an obscure North Country English schoolmaster, John Dalton. He was a self-taught guy. He didn't have much apparatus. He had to make do with what lay to hand. And if you've ever been in England, you'll know it rains. And if you've ever been in the English Lake District, you'll know it really rains. And so what lies to hand is clouds and rain. And so John Dalton observed what was happening and wrote a book, Meteorological Observations and Essays. And this was his attempt to work out what was going on. with rain, water vapor, clouds, sunshine. How did it work? And being an ingenious guy, once he started thinking about that, you sort of think about little bits of water. You can see the drops, but what are they made of? And so you get down to the ultimate atoms that compose this, the chemical atoms, something you probably know as H2O. Well, that's John Dalton's thinking, that there's something that we could call H and something we could call O, and they would fit together. So Dalton pursued his meteorological thinking, and the more he got into it, the more he got into this chemistry of sort of, well, what are these things? Now, Dalton was a Quaker, and Quakers, you know, are people who are very plain people, plain-spoken people, and they love to stay in touch in networks. So Dalton, as a schoolmaster, was recruited into Manchester, big new industrial city, and there to be a tutor in its theological seminary. And there he pursued his inquiries, now in a big town with plenty of people around. And of course, he wrote to other people around the country. He wrote a series of letters. And if you're a Quaker writing a letter, every letter is the same. It's kind of handy. You never say, Dear Joe or Dear Fred. You always say, Respected friend. So the Chemical Heritage Foundation has a unique series of Dalton letters addressed to different people, but every time it's respected friend. And by the time we get from his meteorological observations in 1793 to his 1803 letter in Manchester, he's talking about the new chemical doctrine I have lately promulgated. He's onto something, and he's developing a whole theory of chemistry, of atoms, of what they might be. He's a very visual guy. So he does something unique in its moment, but something with, it's the ancestor of what you see today. And in 1808, he finally publishes his New System of Chemical Philosophy, Part 1. He's got so much he wants to tell you before he can tell you anything that he actually only manages to write part 1 of the whole thing, and even then it's 350 pages. And finally, just at the end, he finally gets to it's atoms, folk, and they kind of look like this. And he draws out for you the atoms and how they look. And if you just mentally substitute for his symbols the letters C, H, O, whatever it might be, the things we're familiar with, that's what Dalton's doing. And for the first time ever, we've suddenly got a language, a way of thinking about it, a set of formulae that advance chemistry tremendously. And from that day to this, chemistry has been done on that basis. If you come to CHF, you can see these books, you can see the unique letters that Dalton wrote about these things, and you can see some really interesting things, one of which is a letter to his friend in Liverpool saying, Respected friend, this is now another guy, he's saying, gee, why don't you tell your friends about my book and get them to buy my book? Because if you're an obscure provincial schoolmaster type, well, the New York Times probably isn't about to publish a review of your book, so you have to say, hey friends, how about buying it? How about spreading the word? So you can see Dalton putting out the word, and you can also see in a wonderful, unique in all the world example of the combination of thrift and savvy, he prints up what we would call a flyer for his book. This is the only copy in the world of this flyer. It's the only copy that's survived. You know, flyers you tend to give to people and then look at it and throw it away, put it in the trash. This one copy in all the world has survived because, being a thrifty Quaker, he used them to write letters on. So on the back of the flyer, he's written a letter to somebody, respected friend, so on and so on and so on. Because it was a letter, the person who received it kept it as a letter. And miraculously today, we have in the Chemical Heritage Foundation this one thing in which Dalton quite clearly says that the third chapter is on chemical synthesis and tends to place the whole science of chemistry upon a new and more simple basis than it has been upon. Very modest words, but absolutely true. He totally transformed our way of thinking about what goes on in chemistry.